So with this video, I'm going to be focusing on Chapter 8 and 9. First thing we want to do, of course, is go over some of the new variables and values and look at their units. So let's see. First we have torque. Torque is just going to be your rotational force. It's going to be this Greek tau. The units are going to be Newton meters. So newtons times meters is your units for torque. We also have inertia, which is just I. Inertia's units are going to be kilograms times meters squared. So inertia is going to be the I, kilograms times meters squared. You also see we have multiple different ways to calculate inertia based on the shape of the object. So that's going to be important. Make sure you're using the right value or formula. Let's see. We also have, we've got pressure, which is going to be force over area. Unit for pressure is going to be pascals. We're going to use pascals when we're measuring pressure. You also have, of course, density, which is the rho. And as you can see, density is going to be kilograms per meters cubed. And those are the new values. I think everything else you should know. So if that's the case, let's move on.
The arm in the figure weighs 40 newtons. The force of gravity acting on the arm acts through point A. Determine the magnitudes of the tension force Ft, the deltoid muscle, and the force Fs exerted by the shoulder on the humerus to hold the arm in the position shown.
So with this question, we're given that the weight of the arm is 40 newtons, so we can write that down. Weight is 40 newtons. And I believe that's all we're given. We also know that the arm is being held in equilibrium. So some of the torques should equal what here? 0, right? And if that's the case, some of the forces should equal what? Also 0. So here's what I have so far. Weight is 40, some of the torques are 0, some of the forces is also 0. We want to find force T first. Now we could try to use the Newton's second law stuff, but you'll do that and you'll find you don't have force T or force S, so we're going to start with the torque rules. So some of the torque should equal 0. We have force S acting on the hinge point, so it's not going to provide any torque, but we've got force T providing torque, and we've got force G, or the weight of the arm, providing torque. So let's write that out. Of course, we know that our torque should equal R, our radius, times the force times sine of theta. That's what I've written so far. So if that's the case, we need the sum of those. So we've got 2 providing torques, force T providing torque that will make a counterclockwise motion. So we're going to use positive. Counterclockwise is positive. Positive radius, which would be 0.08, times the force, which would be what we're looking for, times sine of the angle, which would be 12. And we're going to add that to the other force providing torque, which would be the weight. So it's going to be minus, because that's going to provide a clockwise movement. So minus force times gravity, or actually mass times gravity, which would be the 40 newtons. So 40, the radius is going to be 0.29, and that's it. So that should equal 0. So I've written it sort of sloppy, but that's it right there. Positive for the first torque value and negative for the second torque value equals 0. So we've got that. We can move it around a little bit. So that one side equals the other. So we can move the negative value over and make it a positive value on the left side, or the right side rather. And then we can just do some algebra. So let's do that. So 0.08. And for my torque, or for my force T, I'm getting 697.41. 697.41 is going to be our force T. Let's erase a little bit. No, let's write that to the side. Force T, 697.41 newtons. So we have that. Now we can do our Newton's second law stuff. Sum of the forces should equal 0. Of course, with Newton's second law, we got to take into account both directions or dimensions. So we're going to do the x and the y for that. This is what I have so far. I'll do the x first, the x dimension first. So acting in the x dimension, we have force T, and we've got that force S. So we can just do those values. Let's go ahead and say that force T is going in the negative direction, so we're going to say negative force T cosine 12 equals, let's say, let's say equals force S is x component, and let's just make that positive. So sort of sloppy, but here's what I have. Force T times cosine 12 should equal the x component of force S, and you'll see that those are the only two forces acting on the x dimension. So that's what we have. That's pretty straightforward math there, so let's just plug in our values. We know force of T is going to be 697.41. So for the x component of force S, I'm getting 682.17 newtons. That's what I have. And we can just put that to the side. 682.17. For the y components, or y dimension, we have every force acting on the y-axis. So let's just write out our Newton's second law equation. You've got force of T going up, so let's say that's positive. Force T sine of 12. Force S is going down, so we're going to make that negative. So we're going to do minus force S, the y component of force S, and also minus the weight, which is going to be 40 newtons. So minus 40, and that should all equal 0. So sort of packed in there, but that's what I have. Force T sine 12 minus the y component of force S minus 40 should all equal 0. Plug in our values here, rearrange a little bit. We've got 697.41 for our force T. We do sine 12 minus 40. Move the force S of y to the right side. So force S, y component, and it's pretty simple from there. That's the final equation. The 697.41 sine 12 minus 40 should give us the y component of force S. Let's do the math there. And for my y component of force F, I'm getting about 105 newtons. So we've got the x component, we've got the y component. With that, we could do a little Pythagorean theorem and get the full vector quantity of our force. Vector value, whatever. So we're going to do 682.17, which is our x component, squared plus 105 squared, which is our y component, and that should give us the final value. So here's what I have. The square root of both of those components should give us the final value. So 682.17 squared plus 105 squared. Let's get rid of that. I'm getting 690.2 newtons. 690.2 newtons for our force of S.
A light plank rests on two scales that read force G1 equals 400 newtons and force G2 equals 300 newtons. The scales are separated by a distance of 2 meters. How far from the woman's feet is her center of gravity?
So this problem is very similar to the last one in the approach. Some of the torques should be 0, some of the forces should be 0. Let's look at that. We're given that FG1 is 400 and FG2 is 300, so let's write that out. FG1, 400 newtons, FG2, 300 newtons, and the length of the plank is 2 meters. So those forces are about 2 meters from each other. So let's write X is 2 meters. It's actually not right though. So we've got that. We don't know what weight is. We don't know what her center of gravity is. We want to find that. And we do know that some of the forces is 0, some of the torques is 0. So here's what I have written out so far. Just all we're given, all we know. So we don't know what weight is. We could find it with some of the forces, which shouldn't be too complicated. Newton's second law says some of the forces should be mass times acceleration. In that case, we're going to have some of the forces is 0 because we're in equilibrium. That's what I have so far. I just rewrote that. We've got 3 forces here. We've got FG1 pushing up. We've got weight pulling down. And we've got FG2 also pushing up. So let's do FG1 plus FG2 minus weight should equal what? 0, right? I didn't write it out. But yeah, that's the case. We can move the weight over. So weight is going to be 400 plus 300, which would be 700. So you can write that to the side. Weight, 700 newtons. Now we've got our weight, we can use our torque rules. So some of the torques should also equal 0. The trick here is you're going to set one side equal to 0. So let's say that the left side is our hinge point, our axis. And let's say that some of the torque should be 0. So weight, which is 700, times the distance that we don't know yet. That's going to make it go down, which would be clockwise, make the body fall in clockwise direction. So we're going to say negative 700x plus the FG2 is going to push up, make it go counterclockwise. So positive 300 times 2 should equal 0. So that's what we have there. It may not have been super clear, but we got negative for our weight value. We've got a positive for our force G2 value. We could just set those equal to each other. 700x equals 300 times 2, which is 600. It's not too complicated. We just do the algebra there. 600 divided by 700 should give us 0.857. So 0.857 meters. So not too complicated, and that is the process for that one.
A bicycle wheel has a diameter of 0.7 meters and a mass of 1.8 kilograms. Assume the wheel is a hoop with all of the mass concentrated on the outside radius. The bicycle is placed on a stationary stand, and a resistive force of 120 newtons is applied tangent to the rim of the tire. What force must be applied by a chain passing over a sprocket with a 0.09 meter diameter in order to give the wheel an acceleration of 5 radians per second squared?
So this is a really good problem, similar to the last few, but built on those a little bit. We've got the bicycle. The diameter of the bicycle is 0.7 meters. Just write that out. The mass is 1.8 kilograms. The hoop. The wheel is going to be a hoop, so that's important to write down. Anytime they tell us a shape, say a hoop, a disc, a sphere, a hollow ball, anytime they give us one of those shapes, we know we're dealing with an inertia problem. That's an important give there. We also know that there's a resistive force of 120 newtons, so 120 newtons. And we also know that we're going to apply the force over a sprocket that is 0.09 meters in diameter, so diameter of the sprocket 0.09 meters. And we want to give the wheel an acceleration of 5 radians per second squared, so 5 radians per second squared. And I just wrote out everything we know so far. Let's see if I can put that on there. That's everything we know so far. It's also going to help us to draw this one, so let's do that. Take your time with the drawing. So we've got the wheel, diameter 7.7 meters. A resistive force, that's going to make it go, if I can draw this the other way. Resistive force is going to make it go the negative direction. 120 newtons. We've got to apply a force over a sprocket. You know, our sprocket's going to have a 0.09 meter diameter. So let's just make that totally clear. We're looking at something like this. It might not be the best picture, but that's the idea. So we've got that. We want to find our force that we're applying over the sprocket. We know we're dealing with rotational forces here. So we're dealing with torques. We know that some of the torques should be inertia times angular acceleration. Some of the torques should be inertia times angular acceleration. I wrote that down. You should also be able to locate it on your formula sheet. So we've got two forces. Two forces are providing torques. That's going to be the force over the sprocket and the resistive force. So let's write our forces out. So the force over the sprocket, we're going to do force, which we don't know yet. The radius of the sprocket is going to be 0.045. So here I just said torque, sprocket, or the applied force. I don't know. I'll just leave that. Torque provided by the force over the sprocket. I've got the force that we're looking for and the radius of the sprocket. And you can see that that's just the torque formula. So force times radius. We've also got the resistive force, so the torque of the resistive force, which would be 120 newtons times the radius of the wheel, because that's being applied to the wheel, right? So the radius of the wheel is going to be the 0.7 divided by 2, which is 0.35. And that's the resistive torque. So I'll actually give these little subscripts: resistive torque and the applied torque. So that's what I have so far. This is the sum of our torques. And they should equal the moment of inertia times the angular acceleration, which we know is 5 radians per second squared. So wrote that out, and we're going to have to calculate what the inertia is. So inertia of a hoop, because it told us the hoop, is going to be m times r squared, so mass times radius squared. I'm going to sub that in. Mass of that hoop is going to be 1.8. And the radius is going to be 0.35. I'm going to square that. And that is our final equation. And it's up there pretty sloppy, but we've got force times 0.045 minus 120 times 0.35 equals 1.8 times 0.35 squared times 5 radians per second squared. And I'll write that better. Actually, let's erase it a little bit. I'll erase the drawing. But yeah, same thing. Force times 0.045 minus 120 times 0.35 equals 1.8 times 0.35 squared times 5. And with that, we are just looking at torque applied minus torque of the resistive force equals moment of inertia, mass r squared, times angular acceleration. So let's get that on there. And that's the full thing. That's what we're looking at here. So I've got everything in there. We can just do a little math and be done with it. Quick little algebra. So we've got 1.8 times 0.35 squared times 5. I'm going to add the 120 times 0.35 and divide by 0.045. I'm getting 957.8 newtons. So 957.8 newtons. That's the process there, not overly complicated, just know what you're doing with your new formulas. But yeah, with the variables I give you, it's pretty straightforward to figure out what you need to do. So let's go to the next one.
A solid uniform disc of radius 0.250 meters and mass 50 kilograms rolls down a ramp of length 4.5 meters. It makes a 20-degree angle with the horizontal. The disc starts from rest from the top of the ramp. Find the speed of the disc center of mass when it reaches the bottom of the ramp. Also find the angular speed of the disc at the bottom of the ramp.
So this is another good problem. If you read it carefully, you'll notice it has a similarity to something you've done before, and it looks really similar to your conservation of energy problems you've done on your previous 2 exams. Let's try what we have. We know that it's a disc, which is important. We know that since they gave us a shape, it's sort of a give that we are going to be using inertia. Radius is going to be 0.25 meters. Mass is going to be 50 kilograms. The ramp is going to be 4.5 meters. So length, let's do length of the ramp, 4.5 meters. And it's going to be an angle of 20 degrees. I can just do a little sign. And that's all we know. We also know that the disc is initially at rest. So So that's what we know. I just wrote that all out. And it's also going to help us to draw this one. So let's draw this. So we can draw the ramp. We know the ramp is going to be 4.5 meters. 4.5 meters. The angle is going to be 20 degrees. You know, we've got a disc at the top of the ramp. So that's what we're looking at. Initially at rest, it's going to fall down. We want to find, first, it's the speed of the disk center of mass. So this is important. We're going to just point out the distinction between translational speed and rotational speed. So we've been doing translational speed, which would just be like if the disk sort of just slid down, didn't rotate at all. But in reality, we're going to rotate a little bit as it falls down, right? You see that? Sort of rotates. So we're going to find the rotational speed and the translational speed. So let's do that. To find our height, we're going to do 4.5 sine of 20. I'm going to erase the picture. But the height is going to be 4.5 sine 20. We know that. And we're going to do conservation of energy, right? So gravitational potential energy is what we start with. Let's actually write everything out. So kinetic energy initial plus rotational kinetic energy initial. So we can do KERI maybe, plus potential energy initial. So equal all of that for the final values as well. So here's what I have. At the bottom of the ramp, there's going to be no potential energy. So you can erase that on the final. And initially, at rest, there's no kinetic energy, right? So let's rewrite this. So we took out the initial kinetic energies and we took out the final potential energy. So we've got potential energy initial equals kinetic energy final plus rotational kinetic energy final. So you wrote that, and that's what we're dealing with. So we know potential energy initial is going to be mgh, mass times gravity times height. Kinetic energy we know is going to be, or translational kinetic energy we know is going to be 1/2 mass times velocity squared. And rotational kinetic energy is going to be 1/2 inertia times angular velocity squared. 1/2 inertia angular velocity squared. So that's what we're dealing with. We want to find the translational velocity first. I believe I said the center of mass's velocity. So we're going to change omega squared into velocity squared over radius squared. And I'll show you how we did that as well. So we're going to change omega squared to velocity squared over radius squared, and that's what we're looking at. I just moved that over there, if you can see it. And that is because we know omega equals, velocity over the radius. So if omega equals velocity over the radius, omega squared will be velocity squared over the radius squared. So we plug that in there, and we could really just plug in our values from there, right? So mass is 50, gravity is 9.8. The height is going to be 4.5 sine 20. equals 1/2 mass again. And actually, I believe these are easier if you just don't do any math until you absolutely have to, such as do a little rearranging first. Let's write everything out. mgh equals 1/2 mv squared plus 1/2. Inertia of a disk is going to be 1/2 mr squared. So 1/2 mr squared times omega squared, or actually times v squared over r squared. Let's erase a little bit just to clear it up. But this is what I'm looking at. So I just rearranged everything, just rewrote what we had, and we're going to just rearrange it before we do any math or any number placement. So we'll see that the masses are going to cancel out. So we can erase all the m's. Mass will not be relevant here. So we've got mass taken out. We want to find velocity, so let's just rearrange a little bit. And you could do this by yourself in theory, but I'm going to try to walk you through it. So gravity times height. We've also got 1/2 velocity squared, so we're going to do we've got 1/2 velocity squared plus 1/2 times 1/2 r squared, so we can do plus 1/4 r squared times v squared over r squared. That's what I have so far. That's my first bit of rearranging. That right there in the middle. On the right side, we've got r squared times v squared over r squared. So we can take out both r squareds. They're going to cancel each other out, leaving us with 1/4 v squared. That's what I have there. 1/2 v squared plus 1/4 v squared. 1/2 plus 1/4 is 3/4. So we've got a total of 3/4 velocity squared. Now we're going to move over the 3/4 and the squared, so we're going to do both sides times 4/3 and the square root of both sides. Let's erase a little bit just to clear up what we have. Let's actually give it a little circle as well. That circled is our final equation. We really don't even have to do much more past this. We could just plug in our gravity value and our height value. So let's see. Gravity is 9.8, height is 4.5, sine 20 is 4/3. And for my velocity, we're getting 4.48 meters per second. So our translational velocity is 4.48 meters per second. So that's not too tough. The trick there, because if you try to do the number way, like plug in all your numbers initially, it's pretty tough. You probably get the wrong value like a bunch of times. So avoid that at all costs. Just do all your variables and then do numbers at the end. So we've got that. We also want to find the angular speed of the disk at the bottom of the ramp. We've got our translational speed, and we know our radius is going to be 0.25. So we can just do velocity equals angular speed times the radius. We just divide by the radius, which is 0.25. So velocity over, that should be omega on the other side. So velocity over the radius should be omega. So not complicated at all. Velocity we just found to be the, I think 4.48. So for my angular velocity, we're getting 17.92. So that's that. Not too complicated. Just want to make sure you're being very picky, very very careful with your steps.
A hydraulic jack has an input piston area of 0.049 meters squared and an output area of 0.81 meters squared. How much force on the input piston is required to lift a car weighing 1.6 times 10 to the 4 newtons?
The next one I want to touch, because I'm not sure it's explicitly on your formula sheet, but it's involving Pascal's principle, and that simply states that pressure in is going to be pressure out. So we're going to do that. We know we have an area of the input piston of 0.049 meters squared, and the output area is 0.81 meters squared. 0.81 meters squared. We want to know how much force on the piston, on the input piston rather, is required to lift the car weighing 1.6 times 10 to the 4 newtons. So, and force 2 is going to be 1.6 times 10 to the 4 newtons. So I've just written out exactly what we have. And like I said, pressure in equals pressure out, so you write that. Pascal's principle. Let's actually do this. It's not overly complicated there. The idea though is pressure equals force over area. So what we're going to do is force over area 1 should equal force over area 2. So we know force 1 is what we're looking for. Area 1 is the 0.049. Force 2 we have as 1.6 times 10 to the 4. And area 2 we know is 0.81. So that's what I have. Do a little math in your calculator, and that would be it for this problem. So let's see. So I'm getting for our input force 967.9 newtons. 967.9 newtons. And it makes sense because we could apply a little bit of force on our input surface, and it would all be transferred to our larger output surface. So Pascal's principle in a nutshell, pretty simple. Just wanted to touch it because it's not explicitly on your formula sheet.
The gravitational force exerted on a solid object is 6 newtons as measured when the object is suspended from a spring scale. When the suspended object is submerged in water, the scale reads 4 newtons. Find the density of the object.
So this next one's also really good. We're going to look at it. I'm sure it's been able to look at it a couple of times, but it does bear repeating. It's a really good question. So we know that the weight of our object is going to be 6 newtons. When we put the object in the water, it reads at a lighter weight. Do we know why it reads that lighter weight once we put it in water? And that would be because of the buoyant force. So it reads lighter because of the buoyant force. I'll just write buoyancy. There's nothing special. Buoyant force, buoyancy. We could subtract the 6, or we subtract the 4 from the 6, and that would give us the actual value for our buoyant force. So I'll just write that, put a little square. That 2 newtons will represent our buoyant force. If that's the case, you can look at your formula sheet and you know that buoyant force would be density times volume times gravity. So we know 2 should equal density of water times volume of water times gravity. We know the density of water is 1,000 kilograms per cubic meter. So 1,000. We don't know what volume is. We're going to find it and use it later. And gravity we know is 9.8. So for our, and let's just show you that. So for our volume, we can just plug all those values in, do a little algebra. And I'm getting 2.0408 for our volume. So 2.0408 times 10 to the negative 4th. 0.40 times 10 to the negative 4th. And that would be cubic meters. We've got that. Let's erase a little bit. We know what density is what? How do we calculate density? Density should be mass per volume, correct? So we've got our volume. We know the volume displaced of water would be the volume of the object. So put in the object that places the exact amount of water that has the exact volume that it has. And that was a little wordy, but got that. We know our weight is 6 newtons. 6 divided by 9.8 should give us our exact mass, so we can do that. 6 over 9.8. So I'll just write that here, 6 over 9.8. So here's what we're going to do. We do 6 over 9.8 divided by the volume, which is a 2.0408 times 10 to the negative 4. And that should give us our density. So let's see what we get. And I'm getting about 3,000 for my density. So we've got 3,000 kilograms per cubic meter. Circle that. And that is your final answer. So be sure you know how to do this problem because it is really good and it's going to be seen a lot on your homework, on Espino's sessions, on Daniel's sessions. It's a really good problem.
Water moves through a constricted pipe in steady ideal flow. At the lower point, the pressure is 1.8 times 10 to the 5th pascals, and the pipe radius is 0.03 meters. At the highest point located at y equals 2.7 meters, the pressure is 1.2 times 10 to the 5th pascals, and the pipe radius is 0.012 meters. Find the speed of flow in the lower and upper sections. Also find the volume flow rate through the pipe.
So this is a really good question. I know a lot of people struggle with this one. In the previous years, we've got a tube and water moves through it in a steady ideal flow. You know, at the lower point, let's separate these into sections, lower and higher, right? The lower point pressure is 1.8 times 10 to the 5th pascals. The radius is 0.03 meters. And at the bottom of the pipe, so there is no potential energy. The highest point located at y equals 2.7 meters, so the height is going to be 2.7 meters. Pressure is going to be 1.2 times 10 to the 5th. And the radius can be 0.012 meters. And we want to know the speed of flow in the lower and upper sections, and also the volume flow rate through the pipe. So, not too complicated, but it does seem pretty daunting. Here's what I've written down so far. Let's see what's on there. But yeah, just everything we know. It's broken up into two sections, high and low. So, you can look at your formula sheet and sort of guess what we're going to be using here. I'll give you time to look over that. And you should have found that we're going to be using the Bernoulli's equation. So, pressure 1 plus 1/2 density times velocity 1 squared plus density times gravity times height 1 should equal the same thing for the opposite side. So pressure 2 plus 1/2 density times velocity 2 squared plus density times gravity times height 2. So that's that Bernoulli's equation. And you'll notice it looks really similar to some conservation energy stuff we've done, and that's the idea. So it's conservation of pressure. So we've got that. We can plug in our values. So let's erase a little bit. Pressure 1, let's say that low is pressure 1 and high is pressure 2, so we can plug in all our values. So for pressure 1, we've got the low pressure, which was 1.8 times 10 to the 5. Density of water is going to be 1,000. So 1,000 V1 squared. And we know at the lower point, we're going to say that's our 0 point. So for that PGH, or rho GH, we're just going to say 0 because the height's going to be 0. So plus 0, but you don't have to write that at all. Equals pressure 2, which was the 1.2 times 10 to the 5th. One half density of water times velocity 2 squared. You don't know the velocity. It's 1/2 density of water times velocity 2 squared. And then plus density times gravity times height. So density again is going to be 1,000. Gravity 9.8. And the height here is going to be 2.7. Let's clean that up. So that's what we have, all our values in there. Let's move this back. All our values in Bernoulli's equation. So let's look at this. We realize we're missing two values. We're missing velocity 1 and velocity 2. But we can find one of the other velocities in terms of the separate velocity, right? So take a second to figure out how we're going to do that. And you probably found that we're going to use the continuity condition, which would be area 1 times velocity 1 equals area 2 times velocity 2. I believe we've used this before. We should have. So our area for our lower point is going to be I believe it was 0.03, let me check. 0.03 meters is our radius 0.03, area of a cross-sectional circle is going to be pi r squared, so pi times 0.03 squared. It's going to be our area, pi r squared. Velocity 1 we don't know. Area 2, we're going to do pi r squared with the radius 0.012. So pi times 0.012 squared. And times velocity 2. So that's what we have so far, and that's just a continuity condition. So we can do a little math here. We want to find, let's say we want to find the low point first. So let's make this in terms of volume 2. So you divide both sides by the pi times 0.012 squared. And we should get that volume, or velocity 2, we may have misspoken already, velocity 2 should equal this. Velocity 2 should equal pi times 0.03 squared times velocity 1 over pi times 0.012 squared. Let's clean it up a little bit, make an actual value for that. And if I simplify those terms, we get that velocity 1, or actually velocity 2 is 6.25 times velocity 1. I just simplified that left side. So if that's the case, we can plug 6.25 velocity 1 into our velocity 2 value in our Bernoulli's equation, 6.25 velocity 1. So we're just going to plug that in there for the V2 and do a little math. So let's simplify this some more. 20 times 65, this should be 500 V1 squared plus 0. 5. 500 6.25 V1 squared. And 1,000 times 9.8 times 2.7. Should be 26,460. And this is what we're dealing with now. Just put in all our values and simplify it a little bit. So we've got that. We can simplify that newer value even more. So 6.25 V1 squared would be 39.06 times V1 squared. 500. So I plugged that in, and it's a little messy. Let's move some like constants together, or like values together, so we can move our constants together, of course. 1.8 times 10 to the 5th minus 1.2 times 10 to the 5th would be 6 times 10 to the 5th. 0.6 times 10 to the 5th. So we have 60,000 on the left side. So we can do that. I just put those constants together, the original pressures. So 60,000 plus 500 V1 squared equals 50 times all that plus another constant, so I can move that constant over as well. So 60,000 minus the 26,460. I'm getting 33,540, so we can take that out. And now this is what we're looking at. 30,540 plus 500 V1 squared equals this 500 times 39.06 V1 squared. So we do 500 times 39.06. So simplify that even more, we get that right side to be 19,530 V1 squared. So we've got 33,540 plus 500 V1 squared equals 19,530 V1 squared. We subtract 500 V1 squared from both sides. And we finally have 33,540 equals 19,030 V1 squared. So you can just divide both sides by 19,030. Take the square root. So for our velocity one, we're getting 1.33 meters per second. So our velocity at our lower point is going to be 1.33 meters per second. So that's your velocity at the low point. We also know that, I may have drawn that sort of weird, but we also know that at the other point, it's going to be velocity 1 times 6.25. So the velocity, we're going to do 1.33 times 6.25. And that's because of our continuity equation, which we did earlier. 1.33 times 6.25. Our velocity at the high point, or the other point, is going to be 8.3125. So 8.3125. And lastly, they want the volume rate of flow. And you may have already found it, if I'm not mistaken, but it's on your formula sheet as well, just not super clearly. You're going to do the area times velocity. We know that area's units are going to be meters squared, velocity's units are going to be meters per second. So we can actually show you meters squared times meters per second. That's going to give you cubic meters per second, and that would be the equivalent of volume per time. So your volume rate of flow. So I believe the velocity at the low point was 1.33, and the area at the low point is going to be pi r squared with the 0.03 radius. Pi times 0.03 squared. I'm getting my rate of flow to be 3.76 times 10 to the negative third. May double check that. Let's actually do that with the other value as well. Just double check it. Times pi r squared, pi times 0.02 squared. And I forget even what I said. But yeah, I feel like that's right. That's definitely the process. Definitely hit me if that didn't work. But yeah, that's the idea.
A jet of water squirts out horizontally from a hole near the bottom of the tank. If the hole has a diameter of 0.008 meters, what is the height of the water level in the tank?
Alright, this is another really good one. It's going to use Bernoulli's equation again. You guys should be able to do this by yourself, so I'm just going to walk you through it. We've got, of course, the image with the tank on the platform. We know the hole that the water comes out of has a diameter of 0.08 meters. 0.008 meters. Alright, we want to know what is the height of the water level in the tank. So let's see. course, like I just said, we're going to use Bernoulli's equation again, so we're going to use P1 plus 1/2 rho V1 squared plus rho gravity height 1 equals P2 plus 1/2 rho V2 squared plus rho GH2. So the idea here is that both openings or surfaces are exposed to the Earth's atmosphere, so the pressure will be the same. So the pressure at the top of the tank's going to be the same as the pressure where the water shoots out. So we can cancel out both the pressures. So I just crossed them out. We're going to set the point where the water, or where the hole is when water leaves, is going to be the 0 point. So we can cancel that out on the right side, a height of 0. So I cancel that out, and we can say that the velocity on the left side is going to be negligible because of continuity condition. So A1 V1 equals A2 V2. And if we have a huge area at the top of the tank compared to the small area of the little hole, for the continuity condition to make sense, the area or the velocity of the tank's surface area is going to be super low compared to the velocity of the water leaving the hole. So that may have made a little sense, but the idea is that velocity 1, velocity 2, velocity 1 is going to be super negligible. So we're going to cancel out that velocity on the left side as well. Let's just erase and clear up what we have. We've got PGH1 equals 1/2, or actually rho rather, 1/2 rho V2 squared. So that's our final equation. It's really not much more work than that. The idea here is you have to find the velocity before you can find the height. And you should know how to do that. You should know how to find the velocity on your own. So take the time to find the velocity, and then we'll come back in a second. So you should have had plenty of time to find your velocity. For my velocity, we're getting 1.33 meters per second. So we can plug that into our equation. We know our density of water is 1,000. Gravity is 9.8. We don't know the height. Move to the other side, we know 1,000. And like I said, the velocity should be 1.33. We're going to square that. And we should be able to do a little algebra from there. This is what I have. That is your last little bit of work. And the rest is just calculator. So 1,000 squared plus 5 and I'm getting 0.09025 meters or 9 centimeters. So not overly difficult if you know what you're doing here.